Good afternoon and welcome back to part 2 of our video series dealing with an adiabatic flame temperature. In this video, what we're going to be dealing with is starting from a energy balance equation. We're going to derive the equation to solve our adiabatic flame temperature. And the reason for that is because our overarching question for this video series is basically how hot is the flame in our Bunsen burner where the combustion reactions are taking place. And so in order to understand that, we have to have a way and a means of getting at our enthalpy. And so how do we go about figuring out how are we going to unpack and understand our changing enthalpies that happen from the enthalpy coming in equaling the enthalpy coming out as an adiabatic steady state situation that we have. And so what that leads us to is dealing with the enthalpy of formation, or another way of saying that is the heat of formation. So the enthalpy of formation is basically the enthalpy, the change in enthalpy that happens from the formation of 1 mole of a compound from its individual constituent elements. And so, the heat of formation. So basically we have what are the constituent elements in their most plentiful and natural state at 1 bar of pressure and at room temperature, or in this case at what we're dealing with is 298.15 Kelvin. And so that is the heat of formation for individual constituent components. And so then when we have something like carbon and oxygen forming to make carbon dioxide, what is the change in enthalpy from those individual constituent elements forming to make carbon dioxide, or methane, for example, CH4, carbon and hydrogen? What is the change in enthalpy that happens for those to form in order to make methane as CH4? And so if it's a negative number, it's going to be an exothermic situation, change in enthalpy. So energy is going to be getting released, or heat is going to be getting released for that formation to happen. And if it's a positive number, then that means heat or energy is going to have to be absorbed in order for that formation to happen. And so that's kind of what we're unpacking here. Now, if our temperature was constant, then we wouldn't have to, or if our temperature was constant, meaning it stayed at 298 Kelvin, we would already have our heat of formation known. But our temperature and our enthalpy is not staying constant, because our flame, it's going to be much higher temperatures than what we see for our formation, for our heat of formations. And so those happening at 298 Kelvin, well, our flame in our Bunsen burner is going to be much hotter than that. And so that leads us to having to ask, well, how do we understand how the compounds are going to be interacting in those combustion reactions at much higher temperatures than their heat of formation? So that leads us to dealing with heat capacity. And so the heat capacity, let's go ahead and jot this out here. This is often symbolized as Cp, which is the heat capacity of a compound. And what the heat capacity is the change in enthalpy with respect to temperature at a constant pressure. So that right there is Cp. That's our heat capacity. And since we're going to be dealing with ideal gases in this situation here, we're not going to be worrying about the effects of pressure, because it's not going to be a high pressure situation where van der Waals kicks in and the van der Waals forces kick in and deviate our gases from their normal state of behaviors. And so we can kind of just ignore the effects of pressure in this situation dealing with the ideal gases, which leads us to then saying whenever there is a change in enthalpy, that is going to be directly corresponding to our heat capacity multiplied by any change in temperature that results. And so if we have a small change in temperature, that the product of that and whatever that compound's heat capacity is, that's going to show us what our change in enthalpy is. And so that's what this equation right here is showing for us, is the change in enthalpy is the product of that compound's heat capacity, which again is the change in enthalpy with respect to any changes in temperature at a constant pressure. And so any changes in temperature that happen multiplied by the heat capacity of that compound, that results in our change in enthalpy. So that gets us our means of understanding our changing enthalpy for our compounds. Now, if we were to just have a small range of temperatures, so let's just say we had our enthalpy, a small change in enthalpy, then, and that meaning we have a small change in temperature, if we have just a small range there, then our heat capacity is going to be constant, right? Because if a compound has whatever its respective heat capacity is, if the temperature is not varying all that much, then it can be considered just as a constant. It's not really having an overarching or it's having a negligible effect on that compound's heat capacity. And so if it's a small range, then any change in enthalpy is just that constant heat capacity multiplied by the respective change in temperature that happened. So this is for small changes in temperature. However, we need to be able to understand our situation for a large range of temperatures, because as the combustion reactions are happening and our flame is getting either hotter or cooler depending on how much excess air is getting pumped in, basically the enthalpy coming in has to equal the enthalpy coming out. And so we're going to have a large range and fluctuation of temperatures that is going to be resulting. And so with that comes the integration. We have to be able to understand that as we have a large change in temperature, understanding that our heat capacity for those compounds is going to change as well, because it's going to be getting affected as the larger and larger ranges in temperatures happen. So we have to be able to take the integration of our changes in enthalpy along with the integration of our changes in heat capacity with respect to the changes in temperature. So let's go ahead and write out what that looks like here. And so that then leads us to this. If we just kind of understand, we say, okay, well, let's see, if we have our change in enthalpy, what is that going to look like for a large range of temperatures? Well, then what we would be taking is the integration of our change in enthalpy from one enthalpy to the other enthalpy, so whatever we pick as our enthalpy as a starting point to all the way from the integration to our ending point of another enthalpy. And that is going to equal, here we've got our heat capacity and our, with respect to any changes in temperature, but we have to take the integration of this and whatever our starting temperature is to our ending temperature, right? So whatever the enthalpy is at our starting enthalpy, that's going to be equaling whatever our starting temperature is, and we have to understand what is the integration for all the way from our starting enthalpy and temperature to our ending enthalpy and temperature, whatever that ends up being for our combustion reactions in the flame. As the flame starts at one temperature and ends at another, how have the compounds changed in enthalpy based off of this integration here? And so this leads us to this is our solution here, our equation that is derived to help us understand how hot the flame is going to be. So then the next question is, how does the heat capacity change with respect to temperature? Why does our heat capacity change with respect to temperature? And that's going to be the content of part 3 of this video series. Thank you.